Hello, everybody. We are here to present you about AI and Spark. My name is João da Silva. This is my colleague and friend, Jakub.
Hi.
We'll be presenting you about AI on Spark for malware analysis and anomalous threat detection. We'll be going through how we do it at Avast. The goal of this presentation is to demonstrate how Avast is leveraging AI and big data to burn malware. But for that, you need to start the fire with Spark. So I'm going to quickly go over the agenda of what we're going to do. We're going to talk about what we do, what Avast does in general, how we protect the world, or we try to, how we do malware research and apply machine learning on that. We're going to go through some structure streaming briefly because we are now adapting structure streaming technology. We're then going to talk about how do we use AI on machine learning for anomaly detection on time series in event data. And then we will try to do a small demo at the end, which reminds me to launch the demo because it takes some time to process the data. So I'll just launch it, and then we'll come back to it at the end. Okay, it's running. So thank you, everybody. It's very late at the time. Thank you. Go on.
Oh, actually, we did wanted to start with a thank you because the presentation is about work of many people, but especially we wanted to thank our team. We are from the big data systems, but of course we wanted also to thank people from AI team, especially Jura, who hurt his pinky while he was programming that, Olga, Dimitri, and of course threat researchers and analysts in our company. And actually, what do we do? So Avast is dedicated to creating a world that provides safety and privacy for all, no matter where you are, who you are, or how do you connect. How do you want to achieve that is that with the portfolio of security and privacy applications, we have customers all over the world. It's almost 500 million people. And this generates a lot of data. We have probably the largest detection network in the world where we stop 1.5 billion malware attacks each month with 300 million plus files analyzed monthly and more than 200 billion URLs. And of course, this is so much data that it's basically impossible to go through just by hand. That's why we have our machine learning engine in cloud. So we, of course, collect the data. We, as usual, extract the features. A lot of them are based on the domain knowledge of threat researchers. Then we train models and deploy them and to client applications. For example, one of the systems that we're using is classifying binary files. So out of more than 500 features created by threat researchers, we want to classify it into clean, malware, or potentially an unwanted program. And we do that first by clustering with custom k-means and then applying models per each cluster separately. You can see when it will zoom out that some clusters are almost fully clean, some clusters are almost fully malware. That's why we apply model per cluster, because then the problem space is much simpler, and instead of having one big, super complicated model that is hard to explain, we have a lot of smaller models applied for those clusters. However, how it actually looks under the hood is quite typical.
I'll just briefly explain our underlying data lake, as we call it, Burger. You can ask me at the end why Burger. It just to exemplify is a very simple architecture. We have a client applications with some servers receiving the data. Everything goes through Kafka, through some connectors, and then we dump the data. Currently, our cluster is in a petabyte scale with over 200 servers in the cluster and 4,000 cores. And it's with this underlying structure that we process the data. We also have object storage, customized object storage, where we actually save the binary files that we are researching and we are detecting malware.
Of course, outside of the bigger clusters and systems, we have also smaller ones. One of them is responsible for this feature extraction, clustering, and classification. It handles currently around 700 terabytes of binary files in less than 20 machines. So after the feature extraction step, we also get the features and put them into our data lake. And why do we actually need two solutions for that? Is quite simple, is that as you can see, the top pipeline is much faster, while the data lake part is longer. The custom application is very fast, it's very efficient, it's not many machines. However, it's very optimized code, so it's not easy to experiment with. That's why we have also the data on our data lake, where with Spark we can easily experiment with different clustering algorithms, classification, or metrics, or whatever we want. And due to the fact that we have enough Spark knowledge in-house, basically recreating the whole pipeline on Spark took half a day and 20 lines of code of the clustering and the classification. Of course, it's much slower, and it's not the production ready, but it's especially for researchers to experiment with. So how do we go from files and actual malware to the streams and threat detections? With threats, you can have a three-step approach. First, as a threat researcher, you try to identify a threat. So you analyze the file, you check out the URLs, you reverse engineer some code, and you create the detections, basically the rules that specify that this file is malware of this family. Then operators actually release the definitions of the detections to the client applications, and they do it from couple to couple hundred times per day. And what they're actually releasing are the correlated sets of most often definitions of biggest threats around. The next step is basically that we, of course, try to analyze it on a bigger scale with the data and automate it. So this is basically what AI researchers and engineers do. And when you have a detection and on a client application, it sends us a ping to our backends that, okay, detection happened of this specific malware. So we can create time series out of that we have in this time window this many detections of this type in this part of the world. So operators can, for example, focus on specific anomalies when there is a growth or campaign of specific malware or potentially unwanted program that tries to spread all over the world. But when you have a lot of malware, so like where should operator focus? This can be sometimes a problem. And although the decision cannot be fully automated, we can at least help to focus people their attention where something interesting is happening. So why we need actually short response time is that the campaigns can actually spread all over the world quite fast. This is a photo from our threat lab where basically operators are viewing where and what is going in the world. Let's hope it will play. This is a short video of how our honeypots are contacted. So, for example, we see that our honeypots are contacted by stuff that should not be contacting them. No one should know that this there exists. And we see what is attacking there, where from, how fast, how much, and operators can then adjust what should be the response. So for that, we started thinking about basically custom streaming app, where we went for, of course, Python because of machine learning models. Though the big part of the code was solving stuff already solved, like watermarking, consistency, partitioning. It was written by our AI researchers. It was working well. However, it was a lot of code, so it was not easy to maintain or experiment with, or even to put in production that it will be working all the time. So for that, at this point, engineering stepped in.
So road to heaven, okay, we have this custom app, what we're gonna do, how we bring these models into production, how we make it as fast as possible. So we went on this journey to find a solution, hence the road to heaven. And we found Spark structured streaming. I'm not saying it's the holy grail of streaming applications, but it does have a really good API and it does a really fine job. I'll be talking about several advantages that we found interesting with using structured streaming, and I'll be talking why we chose it for this stage of that project. First, I'd like to mention unified processing engine. This is huge. Structured streaming was released with the goal to unify interactive, batch, and streaming queries over structured data sets. This allowed us to bridge our research and our batch jobs and our models into near real-time results. It was also really nice to be able to collaborate with Jakub and Yuri and the other people from the team, because now we have this underlying dialect, this underlying platform and API that we can all work around and collaborate. While one is working on the UDFs where the models are applied, the engineer can be working on the pipeline and transformations on taking data from Kafka. So it's very easy to collaborate in this environment. Which brings me to end-to-end AI with multiple things. What I mean by that is that, as I mentioned earlier, we have this pipeline, we have this data lake, and this is expensive. This is expensive to compute, too many transformations. What do we do with that? On the top of it, we are applying AI models, and it's very important to be able to, with structured streaming, you compute, you get the result, you only keep the results in memory, and then you distribute those results as fast as possible into many parties that are interested. For instance, we want the researchers to have the latest data that was computed so they can work with that and improve their research. We want to have our monitoring systems being notified when some anomaly actually gets out of order, gets too much, and they can be notified and so on. So it's very important to have all this pipeline, and at the end, in 2.4 release of Spark, to have this for each batch, and then be able to distribute these results into many shapes and forms. Next up, window aggregations and watermarking. This comes out of the box, and we are dealing with time series data and events. It's very important that such a thing like window aggregations are available to us through simple UDF. We applied UDF, we set the interval we are interested in keeping in our streaming query, and from then on, we can process the data. With watermarking as well is that in our case, we really don't want to keep any late data in memory. And in the custom application, a lot of code was just for handling that. Like, we don't want this data, we don't keep it. But now with Spark, we got rid of that code. We just apply one function on the stream, and voila, it comes out of the box. It's a big advantage, I believe, to have such a nice and easy to use APIs through UDFs. Next, resilient streams. So with the custom application, and in many of applications we work nowadays, it's important to be able to execute the code, and if there is a failure, you want to go back to it and not recompute everything. With structured streaming, you just set a checkpoint location, and Spark will handle checkpointing of offsets and batch IDs. It's really, really important, so you don't have to recompute all the data and all the expensive models that you just applied on it. And furthermore, with the structured streaming, there is exactly once guarantees, up to false. And with this, it means that we can just process the data once. We do the pipeline, we apply the model, we get the result, and we do it once, ideally. With those advantages, how is it adoption? How did we go about it? So we had we have a lot of in-house Spark knowledge from researchers, but all were in the batch world. How was the structured streaming? So now I'm going to talk about a few concepts that we learned along the way. First, the idea of unbounded table. It's very important because the data comes in, is added to the input table, is computed the result, and that is kept in memory. All the rest of the data, which you don't need, is dropped. So you just keep in memory the data and the results you are interested in. This is important. Which other good property is that you can take a stream, you calculate, you do your calculations, and you have a result. But if you take the whole data and you run a batch job on it, you should get exactly the same results. And with that means we can take the data, apply a batch job, train the model, check the model results, and then you can use it in structured streaming, and you should get the same results. So we can train, research in a batch mode, and then deploy it in a streaming mode. Triggers. Triggers were quite interesting because it's actually the underlying of how structured streaming work. Based on triggers, it will choose which engine to use for execution, and will choose how the intervals of your data processing. I'll just go quickly over them that are interesting. So processing time triggered. Every interval, in this case 5 seconds, can be set milliseconds, any unit of time. You can, it batches your data, waits, processes, and then after that time, it starts the next batch. The default is 0, which means structured streaming will, as quickly as possible, once the first micro batch finish, start the second one as quickly as possible. If you have the interval, then it will wait and grow the batch. Second, we have once, as the name says, it executes the query once, it finishes, exits, and any data arrives after that will not be processed. It's very useful for debugging and for testing. And finally, there is the continuous trigger, which with a low latency mode of processing, which brings me to micro-batch processing versus continuous processing. And micro-batch processing is what we are mostly used to. It uses the underlying micro-batch execution engine. It has exactly once guarantees, up to false. Of course, there are many things you have to handle for that to happen, but it's there. And it has a higher latency. It's the order of 300, 400 milliseconds it takes to process the micro-batch in our case. With the recent addition, we have continuous execution engine. It's experimental mode still. We'd like to see it developed a bit further. There were some talks today and yesterday about that, which were interesting. And the main thing in this case is that we are trading guarantees for latency. So it's good that you have a choice to execute in which engine it better suits your use case. And in some cases, you want it as fast as possible. In some cases, the latency, in our case, of micro-batch is acceptable, and we have a good trade-off of more guarantees on the data processing pipeline. So those were the points. So just because every talk is nice to have a before and after, this is our custom application. You cannot read it, and that means it's too big, too messy. Not messy in a bad code way, but it's just too much stuff that we should not have to write to have intelligence in our applications. So this is how it looks like, more or less, after adopting structured streaming. As you can see, reading from Kafka, gone. Applying models, transform, give your UDF, you get the results. It's so nice to work with this API. And so now we see how some ideas of how we apply streaming and how we use structured streaming, or what makes us use structured streaming. Now I'm going to pass it on to Jakub, and he's going to show us how the AI and the machine learning works behind of it.
So again, how do we detect anomalies in our time series? What we want to really do is we want to know how to quickly identify campaigns of malware or potentially unwanted programs. You can, when you have a time series, you can of course do it the classical way. We just try to find outliers, missing data, or this kind of stuff. What else you can do is try to use machine learning, of course, when you try to predict the next step in time series, and when it appears, you compare it with the observed value. For that, of course, we went with neural networks, not only for marketing purposes. Out of our comparison, we just ended up with useful and working architecture. Of course, we realized that there are some more typical ways how to deal with time series with, for example, autoregressive models, but still, for us, worked the other option. So when you have a model, you want to train it. So when you have thousands of those time series and you want to train 1,000 models on them, you can do it sequentially on one machine. That's fine. It just takes a lot of time. However, with Spark, you can do all of it in parallel if you have a big enough cluster. With previously map partitions and currently with the pandas UDFs, you can just encapsulate your whole model training in one function and run it in parallel on as many nodes as you have. Of course, if we went for a bigger model, really big model, instead of many small ones, we could use distributed training with, for example, TensorflowOnSpark that we have running in our cluster, but we don't find many use cases for that big models to require distributed training. And if we need a big model, we use our GPU cluster for that. What Joao already mentioned is that this unified part is really, really nice for us, that with, for example, those pandas UDFs in parallel for these thousands of time series, we can take the same API, just change how we read the data, how we write the data, and it's the same code. So it's super easy to test the models, train them, and then deploy them and validate on batch, and then just read a couple of lines of code and deploy on a streaming application. And this is what we're going to show, how it worked.
Okay, moment of truth. Still running, I apologize. But I was prepared for that, and we should have a previous output here. This is what it should look like, what is running now. You guys can hear my CPU? We are actually burning malware, you know. So this is what it should look like. From that, if we didn't get any true for is anomaly column, we have only showing top 20 rows. But the idea is if we would get true on is anomaly, we would then send it to notifications, send it to the researchers, make some nice graphs. Everybody likes graphs. For the code walkthrough, this is the essential of the streaming part. As you can see, it's just the same as the before and after code we show with a few more things. But what I like about this is that, in my case, the apply, these UDFs are UDFs which we apply. I don't understand what is inside of those UDFs.
TensorFlow.
I'm the engineer, so there's a scientist. But as you can see, we do have some small boilerplate on the top, but it's really small comparison with the initial approach up we had. Going back to the slides. So challenges. Like we were looking for a road to heaven. We almost found it, but there are a few steps, a few challenges along the way to get there. The main issue we can see is that when you're working with this ecosystem, you have, for example, you have pandas, then you have Spark data frames, then you have Arrow underneath, and you have a bunch of libraries. And in some versions, if you don't have the right version of the library, or if the Spark version is not compatible with what library you want to use, sometimes you have errors that you cannot really figure out what's the problem. And by that leads me to unexpected behavior, or it could be just unknowns for us because we are just recently started using Spark streaming. For instance, when we started working on this, there was a situation where the disk just was was filling up, and we want still to understand why the disk is filling up. We checked the checkpoint directory, not big. We still looking for a solution for that. And silent failures is when you get the error, conversion error of the timestamp. but it doesn't actually, the stack trace doesn't actually tell you where was the error. It just shows you it was somewhere in, for example, it was with Haro, somewhere in the Haro call, you have an error, but it doesn't tell you the top level where it comes from.
But sometimes also it happens that you have no error at all, and it still should work, but it doesn't. It doesn't tell you even that.
Mysteries. Next takeaway. So we have to finish the talk in a good note. Some of the takeaways was really easy for me to collaborate with the science team. Just this platform, unified API, it really rocks. The guys really did a good job in putting this together. Excellent toolbox for anomaly detection. There is windowing, watermarking, easy API, very nice. Easy ML and AI integration. Well, earlier in the challenges, we mentioned that sometimes it can be difficult with those things. But when you are actually writing the code, the TensorFlow code that reads the models, that gives you the results, that part is actually easy. It's a simple API, and it was cool. And of course, parallelism, as Jakub mentioned earlier, is very important because we are working with hundreds of models on this for different types of detection families. So, thank you very much. You really made it to the end, 5:30, last talk. It's really special to have you all here, that you made it to our talk. Thank you.
Thanks a lot.
Any questions?
Just can you give me a number on the throughput you can achieve with your system?
No, not yet.
Some concern were raised with the maturity and robustness of Spark structure streaming, in particular
Yes.
when you have heavy topics with lots of partitions. Did you really test and assess the exactly once semantics? Are you confident in that?
I'm not. That's why I said exactly once up to false. Because it's exactly once is always tricky. Many vendors, such as Kafka Streams, they say exactly once, like structured streaming, but there are many things you need to look after and take care to actually make it happen, but still you cannot actually make it happen.
Okay, and a quick second question. The windows you deal with, few minutes, are you going to, what are the biggest time frame you work on live data?
The moment is 60 minutes, right?
No, actually, depending what we need. In this case, we needed like shorter windows. But when we need very long windows, we basically write it back as a sync to Kafka when we can have like days of windowing. So some models require 3 days of history, right? So we just sync it back to Kafka and read in a separate application, which is also super short because it's again another 5 lines of code to read from Kafka and start there again with the Spark streaming.
Are you using the trained models inside the clients? Inside your antivirus, for example?
Not in this case, no. Mostly we try to make the decisions super fast. So it's much easier to deploy the definitions as basically set of rules. So we have some models, but not many of them on the client. We have many steps of how we deal with malware. We try to make it from the fastest place on the client. Then when we try to run the file, for example, in the sandbox, and when we are still not sure but the file is still suspicious, then we try to send it to our backends and then analyze them. It's just faster this way and more robust.
Why not the other way around? Because sandboxing takes hour.
We also have sandbox in the cloud, but we don't want to collect too much data that people might consider private, right? That's the main reason. We can be suspicious because we haven't seen this file that's encrypted anywhere else in the PC, but you can have a valid reason for that, so we don't want to send it to us until we're really, really sure that this is very suspicious. That's why we run sandbox also on the client application.
Sorry, last one, a quick one. You said that at the beginning that it was slow, actually. So you use it basically for experimenting, prototyping, and then you move to other. Is it the way you will keep working on? Are you going to use?
Not everything. We have many moving parts in the whole pipelines. One of them is implemented as this optimized cluster. That's why for that we need speed in this part, but this is just one of our machine learning systems that we need fast and optimized. In case of Spark streaming, this is still fast, and we still have machine learning models, right? We still use the main data lake for that instead of optimized custom application.
Hi, thank you for the excellent presentation. So I have two questions. First is how involved is the work to embed TensorFlow into that Pandas UDF for training, both training and inference? And then the second, you mentioned that the model is basically trying to have a time series as an input and then predict the next step. So is missing data important and very difficult to handle in this case?
Okay, so the missing data, of course, is important, but most anomalies that we consider important to look at are rather big, so we don't have that much of missing data overall. And could you repeat the first question?
How involved is embedding TensorFlow?
Yeah, this is actually super simple. Because you just wrap your whole TensorFlow function inside of this Pandas UDF, and that's it. So you can have your training function for a model just with annotation. And it doesn't matter if it's Pandas UDF or map partitions. Basically, you have a function that does all the steps per group, and you just output Pandas UDF with the model.
Something like that.
This is simplified version when we just read actually the model from a data frame into the inside of the Pandas UDF and then apply it.
Yeah.
And that's for prediction, right? For training.
It's also you can store it as a for example in Keras you can store models as a JSON inside of a data frame if you want. So you can have multiple models in parallel where you in the end store them as a data frame in one partition if you want.
But you use also the structured streaming for training? Or
No,
that was
not in this case. This is for serving,
prediction.
yes. We haven't tried yet training on streaming.
It's a good idea.
Yes.
Just a quick follow-up.
Sure.
So you're basically parallelizing the models and training several different models with several different parameters.
Yes. But it's not necessarily, for example, hyperparameter training. We can do it inside even Pandas UDF, right? If you want. This is specifically set of different models trained in parallel on different time series.
How many time series do you train upon? Is it like malware families, which are like hundreds, or specific versions of malware, which are?
Well, I'd rather say it's malware families. It's more general, but then we try to split it for example, countries or system versions, this kind of stuff. So, okay, you can have hundreds of malware families, but then it grows if you add another layer of this. So, like system version of or basically country.